Okay, hi everybody. So today we're going to start the second part of 4.3. And the second part of 4.3 has to deal with concavity. So at the first part of 4.3, we talked about the first derivative test, and we talked about minimums and maximums and how to test for mins and max using that first derivative test. So today we're just going to keep jumping on that. We're still talking about the shapes of our graphs. So we're still going to be talking about the shape of our graph, but now we're going to talk about what concavity is. So first we're going to start off with the definition. So the definition for concavity is if a graph f lies above its tangents on an interval I, then it is called concave upward. And the way I like to think about concave upward is by a happy face. So for example, an example of a happy face is like a happy parabola. So that's saying that if our function lies above its tangent, so what exactly does that mean? So if we kind of look at the example that we have here, this graph that we have here, if we were to draw tangent lines, right? If I start from the left-hand side, right here, my tangent lines are actually, let me grab a color so it stays. My tangent lines here are above my function f. And then all of a sudden they start to hit below my function f. So if we look back at the definition, it says that if the graph of a function f lies above all of its tangents, then it is going to be called concave upward. And if a graph f lies below all of its tangents on the interval I, then it is called concave downward. And so the best way to remember this is that concave downward is associated by this downward, that was a horrible graph interpretation of it, but it has the shape of basically a sad face is what I like to identify it by. And it means that my function is actually below its tangent lines, and that has to do with the part that's over here. So if we look at this part right here, when we drew our tangent lines, they were actually above our function. Our function is the one in orange, and my tangent lines are actually above. And then all of a sudden, right over here, my tangent lines are actually below that function f. And so that's what it means to be concave upward versus concave downward. And concave upward has it has the same shape as a happy face. So every time you're thinking concave upward, we're thinking happy face, and every time we're thinking concave down, we're thinking sad face. So we can think about from here to here, let me get a different color. I know that I'm going to be concave downward. And then from here to here, I'm going to be concave upward. Okay, so far by that definition, we know that from this part here, we're concave down and concave up on this side. Okay, so now that we went ahead and talked about what it means for something to be concave up and concave down, our next definition is going to be an inflection point. And so what is an inflection point? So the way that we want to think about an inflection point is an inflection point is a point P on some curve y equals f of x, or any function really, that it's a point where it changes from concave up to concave down. So for example, if we read the definition, it says, it is a point P on a curve y equals f of x. So for example, in this random example of our function, here is y equals f of x. Okay, so that's y equals f of x. And the point that's considered an inflection point for us is this point right here. And this is our point P, inflection point, because when our function is continuous there, and here it changes from concave downward to concave upward. So anytime you have a concavity change from concave up or concave down or concave down to concave up, that point where that happens is going to be called an inflection point. So this point right here is known as our inflection point. And so this is really similar to the thought process of a critical point. So before, at the beginning of 4.3 and then 4.1, we talked about critical points. And those are points where they might hit maximums or minimums. And so our inflection point is a point where it changes from concave upward to concave downward, or vice versa. And so that's where that change happens. And so that's what we're going to define as our inflection point. And the next thing we're going to actually talk about is, how do I actually go about finding these? How do we go about finding concavity? Yes, we can look at a function and say, hey, right here, it's concave downward, and here it's concave upward. We can always do that. But how do we do that if we don't have the graph? And so the way that we're actually going to go about that is by doing a similar test how we did our first derivative test, but we're going to be using what's called a concavity test, and that's going to have to deal with the second derivative. So we'll do that in the next page over. Okay, so now we're going to talk about how we are going to test for concavity. And so testing for concavity is actually very similar to the way that we did the first derivative test, where we took the derivative, set it equal to 0, and then tested those intervals to see if they were positive and negative, and that told us whether they were increasing or decreasing. And so for the concavity test, instead of doing it on the first derivative now, we will be doing it on the second derivative. And so for the concavity test, we have that if our second derivative is greater than 0 for all of our x's in that interval, the graph of x is going to be concave upward. So if our concavity is positive, if we test that interval, if we test the second derivative and that interval there is positive, then we're going to have an upward shaped concavity. And then if we have our derivative is less than 0, then it's going to be downward. So this is, again, very similar to how we would do the first derivative test. So for the first derivative test, we took the derivative, we set it equal to 0 to find our intervals of increasing, and we set it equal to 0 to find our critical numbers. And then from our critical numbers, we separated the real number line into intervals, and then we tested each interval to see if it was positive or negative on the derivative. And we're going to do the exact same thing now, but with the second derivative. So for example, we were to discuss the concavity of this function f. And our function f here is f of x is equal to x cubed minus 3x squared plus 1. So let's say we were given this function and we wanted to just talk about the concavity. Now, more than likely, I'll ask you the question of concavity along with the question of minimums and maximums. But just for this example, I want to show you how to find the concavity. So in order to find the concavity, we want to test it on the second derivative. So that means we have to take the first derivative and then the second derivative. So right now is a good idea to pause the video and take the first derivative of this function, and then go ahead and take the second derivative and see if your answer matches mine. So go ahead and pause the video and try it on your own. Okay, so my first derivative is f prime of x, and my first derivative is 3x squared. I'm just doing the power rule here, minus 6x. And because I want to know about the concavity, that means I have to take my second derivative. And now I'm going to take the second derivative and I get 6x minus 6. And so now what do I do with this second derivative? I do the exact same thing like I did with the first derivative test, and I'm going to take my second derivative and I'm going to set it equal to 0 because those are going to give me my potential points of inflection. And I don't know for sure that they're points of inflection until I determine whether they were concave upward or concave downward. So, for example, what I mean by that is we learned that our first derivative is greater than 0, then it's going to cause a concave upward shape. So that means if we come back to this one, that means that here our second derivative here was greater than 0. And here where we were concave downward, our second derivative was less than 0. So this one was a point of inflection because it changed from concave downward to concave upward. So we need to test whatever point we get when we set the second derivative equal to 0 to see if there's anything like that happening. Because if there's not something like that happening, let's say we test the second derivative and we get positive and positive, then that point is not a point of inflection, because a point of inflection is the point where it changes from concave downward to concave upward, or concave upward to concave downward. So we need to check and test that. So if I solve for this, I'm going to end up with x equaling 1. Hopefully we all got that. And so now our job is to test this. We need to test this point to see if that's an actual point of inflection. So we will draw our number line just like we have been before, and we're going to test it at 1. So our testing point is 1 because that's a potential point of inflection. And now what we're going to do after that is now we're going to test a point here. And just like before we tested it on the first derivative, here we're going to be testing on the second derivative because we're concerned with the concavity of the function. So we're going to test a function here, and we're also going to test a point here. So here we want to test a point. A good point to test is maybe 0, and a good point to test here is 2. So what I want you to do here is I want you to pause the video and figure out whether this was positive or negative. So hopefully you did that, and when you plugged in 0, that's pretty easy. You have that our second derivative is negative. And so that means we have a concave downward shape from 0 to 1. I mean, from negative infinity to 1. And here we have a concave upward. Perfect. So if we wanted to discuss the concavity, so we would say that our function is concave downward from the interval negative infinity to 1, and concave upward from 1 to positive infinity. Okay, and so that's how we would discuss the concavity of a function, just by saying the intervals. And this tells us a lot to do. This tells us how our function is behaving so that we are able to easily graph it, which is what we're going to be doing in 4.3. Okay, now let's move on to another example. I want you to find the concavity of the function f of x is equal to 8x squared plus ln of x. Okay, so for this example, if we're looking for the concavity of a function, what we want to do here is we're going to end up wanting to take the second derivative. So go ahead and pause the video and find the second derivative of it, and maybe even go ahead a little further and find your potential points of inflection. So if we take the first derivative of this function, we will get 16x plus 1 over x. And then if we take the second derivative of this function here, we'll get 16 minus 1 over x squared. Okay, so hopefully everybody got that. And so now our job is to take f double prime of x and set it equal to 0 in order to find those points where we need to test. So then we'll get 16 minus 1 over x squared, and we'll set it equal to 0. And when we set it equal to 0, hopefully you end up with x is equal to plus or minus 1 over 4. So if we solve for x, this is what we get. But here we have to be a little bit careful because we also have to talk about, hey, what's going on in this function here? So because we are dealing with the Allen function, right? In order to find our critical points, our points of inflection, we need to make sure that whatever we're plugging in, one is defined and is continuous at that point. But since Allen is only true for positive real numbers, this means that we are only defined for anything with x being greater than 0, greater than or equal to 0, sorry. So then that means that we are actually only concerned with having x plus x being 1 over 4, not x equaling negative 1 over 4, because that's not defined in our function. So that means we actually only have one point to test, and that point is 1 over 4. So if we take a look at this function, right, the point that we're actually going to test is 1 over 4, and so let's put that somewhere over here. Now, one thing we do want to be careful is when we're testing points, we can't just say, okay, if I were to test something before, before 1 over 4 on the left-hand side, so right over here, then maybe I would want to do something like 0, or I want to do a different function, like, for example, -1 or -2. Well, I can't do that because, for one, my function is not defined here. And we can't actually test 0 because if I test 0, then he'll end up here in the denominator. So we have to be really careful with testing points in this scenario because we're not actually testing it on the whole entire real number line anymore. Now we're actually going to be doing it on the number line all the way over here on the right hand side is fine, but now here I have my point 0, where I want to test something between 0 and 1 over 4 because of that ln function. So I want to be careful with what points I plug into this part and what points I plug into this part. Okay, so I'm going to go ahead and do that. So go ahead and try to think of something that will come into here and come into here. The two that I will use are going to be, I'm going to be using f double prime of 1 over 8. Is it smaller than 1 over 4? And then I'm going to also be testing f double prime of 1. Okay, so if I test f double prime of 1 and f double prime of 1 over 8, go ahead and pause the video and see what you get. But you should get concave downward here and concave upward on this area. And so that tells us that if we were to discuss the concavity, we are concave up from -1 over 4 to infinity, and we are concave downward from 0 to 1 over 4. So hopefully you were able to get that. So a lot of this has to do with a lot of practice, so just keep practicing all of this. And then now we're actually going to go into what's called the second derivative test, which I don't want you to confuse for testing for concavity. The concavity test is just testing the second derivative and testing to see if your function shape is concave upward or concave downward. But the second derivative test, which I'm going to talk about in just one second, has to do with finding our extrema of our function. So we're testing our extreme points in our function. So I'll move on to the next page for that. Okay, so now we're going to talk about what's called the second derivative test. And the second derivative test here tells us about our minimums and maximums of our function. So I know that we use the second derivative to test for concavity in what we learned just a few seconds ago. But for this case, we can also use the second derivative to find our mins and max. And that has to do with a lot with the fact that when we find the concavity of a function, we can determine the shape of the graph. So like, for example, here I can tell that we are concave downward, right? Because it makes that kind of sad face kind of shape. And then it starts to become concave upward. So the second derivative test says if f double prime is continuous, so that just means that we're able to take a second derivative near some value c, and remember that c could be any value. For example, this here can be our value c, or down here can be our value c, just a critical point. If we find out that c is a critical point and the second derivative is greater than 0, so remember, if the derivative is greater than 0 at that point, that tells us that we are actually concave upward. And if we are concave upward, we're making this sad face, this happy face shape, right? So when we make a happy face shape, we have a valley. And so that means that we are actually at a minimum of our function. So that says that if we have a critical point by taking the derivative, set it equal to 0, and we find out that the second derivative at that point is actually greater than 0, then it's going to be a minimum. And so that tells us that, for example, here, let's say this is our value c, right? This is a real minimum. And then at this point right here, our f double prime is actually greater than 0 because we're concave upward. And it also happens to be that if you also have a critical value here, and if our derivative is less than 0, which means that we are actually a downward parabola or a concave downward, then it has a local maximum, which makes sense because right here, at this spot here, we have a real maximum. And here, we're concave downward, which means that our derivative is actually less than 0. So these are really good concepts to know and understand. And so just keep that in mind. So you don't always have to, plug in values or test intervals of increasing and decreasing. In fact, I would encourage that if you have a problem where you have to take the second derivative anyways, because I ask you about the concavity of the function, then go ahead and try to see if you can make the second derivative test work. So now I want to do an example. So let's do an example. So let's say we have the function y equals x to the 4th minus 4x cubed. I always love to start with simple parabolas or polynomials just so that you can kind of get a hang of what's going on. And so I want you to use the second derivative test in this case. So go ahead and try it on your own and see if you could come up with anything. Pause the video and then, click back to make sure you were on the right track. Because it's not very hard, I believe you can do it, but it's a good idea to try it on your own anyways. So if we wanted to use a second derivative test, that means that we have to find two derivatives of the function. So then we have to do y prime is equal to find our first derivative, 4x cubed minus 12x squared. And then now what we want to do is In order to do the second derivative, we actually need to first find our critical points. We know that eventually we're going to have to find the second derivative, but the second derivative test says that we are going to test our critical values on that point. So in order to do the second derivative test, the first step is to find our critical values of the function. So the first thing we need to do is get our first derivative, set it equal to 0, and then we'll eventually take the second derivative and then test those critical values on the second derivative. So let's go ahead and take this and set it equal to 0. So we're going to get 4x cubed minus 12x squared, and we're going to go ahead and set that equal to 0. So if we go ahead and set that equal to 0, we can easily factor out a 4x squared. We factor out a 4x squared, we are left with x minus 3 equals 0. So that means our critical points are actually 0 and 3. Okay, so these are our critical points. And since we're dealing with a polynomial, there are only critical points. So these are our critical points. Okay, perfect. And so here, in order to do the second derivative test, we won't do that line test right away. What we'll actually do is we'll take the second derivative now. So we'll go ahead and take that second derivative of our function. So our first derivative is up here. It's our 4x cubed minus 12x squared. So our second derivative is going to be 12x squared minus 24x. Okay? And now what are we going to do with our second derivative? Now, what we wanted to do is we wanted to test our critical points. So instead of using that number line to determine whether our intervals were increasing and decreasing and determine if those were interval mins and maximums, what we're going to want to do now is we're actually going to test our critical points in that derivative. So we're going to plug in f double prime of 0, and we're also going to plug in f double prime of 3 into our second derivative and determine whether that's positive or negative. So we would do 12 times 0 squared minus 24 times 0. And then here, this one's easy enough. It's just 0. So this is actually what we call inconclusive. And so that means that we need to do the first derivative test. And sometimes that happens. Sometimes you'll, run into a point where the second derivative doesn't work, and that's okay. You know how to do the first derivative. It's just sometimes if it does work, then the second derivative test might be a little bit easier to do because you don't have to do test points or anything. And so then we would do it again on 3, and then we get 12 times 3 squared minus 24 times 3. And if we evaluate that, we get 108 minus 72. And right away, you can tell that this is actually going to be greater than 0 because 108 is much larger than 72. And so because it's greater than 0, we have a minimum. So this is going to give us a minimum. And so I'm not actually going to find out whether 0 was a local min or max. What I want you to do is on your own, use the first derivative here in order to determine whether that was actually a minimum or a maximum. So try it on your own. Okay, so now let's do an example where we have to implement finding the intervals of increasing and decreasing, find our mins and max, and then find our interval of concavity and our inflection point. So in order to do this, right, so in order to do part A, right, we want to find our intervals of increasing and decreasing. So in order to find our intervals of increasing and decreasing, what we want to do is take the derivative of our function and then determine whether our derivative is negative or positive in certain intervals. So go ahead and try that on your own. So first find the derivative of f prime of x, which is going to be 15x squared minus 15x to the fourth. Okay, and now once we have that, we can now find our critical values so that we can split the interval into parts, because remember that our critical values tend to split our intervals from increasing to decreasing. So let's go ahead and set the derivative equal to 0. And so that's going to be, we can factor out a 15x squared. And then we end up with 1 minus x squared, which is equal to 0. And then this here is going to yield a critical value, which is x equals 0. And then here we're going to end up with 1 minus x squared equals 0. And so then we're going to get x equals plus or minus 1 as our other two critical values. So these are our critical values here. And now what we want to do is now test these values to determine whether our function is increasing or decreasing at those values. And when we do that, we'll basically get part B as well, for the most part. So now we can split the graph. So we have 0 here, we have 1 here, and we have negative 1 here. So go ahead and on your own, test points in your derivative. Here, 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 and here, so that you can tell if they're increasing or decreasing. Now test that on your own. I would recommend to do 2, negative 1/2, positive 1/2, and then maybe 2 again, positive 2 though, in this case. So go ahead and take a minute to just test those values. And hopefully once you've tested them, you'll determine that here you get a negative, here you get positive, positive, and then a negative value again. So what does that tell us about our function? It tells us that here we're decreasing, here we're increasing, here we're increasing as well, and then here we're decreasing. So as you can tell, not all the time will a critical value make a jump from increasing to decreasing right away. It could be the case that it doesn't always happen. So for example, here we would have expected this to make right here in the middle to have something where it's increasing and then decreasing and then increasing to decreasing, so that we get, like, for example, a maximum here. But it actually doesn't happen, and because it doesn't happen, then there's nothing that actually happens there. It's not going to be a minimum or a maximum. So our intervals for increasing are just going to be right here in the middle, which is going to be from -1 to 1. And then our intervals of decreasing are going to be from -∞ to 1. And then we're also going to do it from 1 to infinity. So hopefully we all got that for our intervals of increasing and decreasing. And now our job is to find our minimum and our maximum value. Now we know that a minimum happens here at -1, and a maximum also happens here at +1. But now we only know that they happen there. We actually need to figure out how high they go. And so in order to figure that out, we need to evaluate f of -1, and we also need to evaluate f of 1. And when we evaluate f of -1, remember that we always plug this value into the original function. So go ahead and do that. And so hopefully you end up with the value -2. So our minimum is at -2. Because remember, our minimum is the y value of our function. It just so happens to happen at -1. And then if you plug in a +1, we get 2. So our maximum is at 2. Now for the second part of this problem, they wanted us to evaluate the intervals of concavity. So they want to know when it's concave up and when it's concave down, and also where those inflection points happen. So now we have to report an ordered pair for those inflection points. So in order to do that, we need to find that second derivative. So we need to find f double prime of x. Now I want to mention something real quick. I decided that I was going to do the first derivative test here in order to find the minimum and the maximum values, but we didn't have to do that. You could have also done the second derivative test here, and I encourage you to try it on your own to see what you get, and to see if you get the same thing. You should. And so now for f double prime of x, what we want to do is take the second derivative of this, and remember our first derivative ended up being 15x squared minus 15x to the fourth. And so now we have to take the derivative of that. And if we take the derivative of that, we're going to end up with, 30x minus 60x cubed. And remember, in order to find our points of inflection, we do the same thing that we do with our concavity test. And we take our derivative, our second derivative, and we set it equal to 0. Easy peasy. And now we can factor out a 30x. And now when we factor out a 30x, we can factor out a 30x, which we get 30x, and then we get 1 minus 2x squared, which is equal to 0. So from here, we get that this is going to, one of our critical or our points that we are interested in is at x equals 0. And then another point that we're interested in is we need to find 1 minus 2x squared, which is equal to 0. And if we solve for this, we'll actually end up with x is equal to plus or minus 1 over root 2. So hopefully you got that as well. And now our job is to test these values. So we want to test at 0, 1 over root 2, and negative 1 over root 2. So go ahead and do that and test the points there. And remember that here we're actually testing on our second derivative. And so for this, we're plugging into our second derivative. Go ahead and try something on this left-hand side, something like f double prime of negative 1. Here I would test something in between negative 1/2 and 0, which might get a little bit tricky, but you can do it as well. Also same thing here. And something over here on the right-hand side. So for example, evaluate f double prime of 1. And so remember, you're doing these on the second derivative. So what I would do for these is, maybe you don't know what negative 1/2 is equal to, negative 1 over root 2 is equal to. So go ahead and grab your calculator and go, oh, okay, let me do 1 over root 2. And that's roughly about negative 0.707. And so this one here is roughly about 0.707. So go ahead and plug in maybe a decimal value between these two and figure out what they are. And then I'll go ahead and let you do that on your own. So go ahead and pause the video and try it on your own. And here you should have gotten concave upward. Here you should have gotten concave downward. Here another concave downward, and then, here. And then here you should have gotten concave upward. And then here concave downward. So then this tells us that our concave up, our intervals of concave up are from negative infinity to negative 1 over root 2. And then we're going to union that with our other interval of concave upward, which is right here, is from 0 to 1 over root 2. And then for concave down, we'll do negative 1 to 0 and union that with 1 over root 2 to infinity. All right, perfect. But remember that they didn't just want to know the intervals of concave up and concave down. They also wanted to know the inflection points. So because they wanted to know the inflection points, we know that these three here are actually our inflection points because that's where it changes from concave up to concave down. Now our job is to find out where they happen in the graph. And then I'll explain why these are actually helpful in a second after we finish this. So then for our inflection points, what we want to do is now we want to plug in our original points, our points of inflection into our original function. So we want to evaluate f of -1/√2 to our original function. You want to evaluate f of 0, and then we want to evaluate f of +1/√2. So go ahead and put these values back into our original function and evaluate what you get for that function. So once we do that, hopefully you'll end up with -7/4√2. Plug in 0, you get 0, and then here we get 7/4√2 as well. So our inflection points are -1/√2, -7/4√2, 0, 0, and then +1√2 over 7/4√2. So there's also another example I wanted to go over. I'll write it down here in the notes, but I'll have you guys kind of do it on your own and just see if you guys can get that practice. I won't actually do it on this video just because there's a ton more videos that I still have to do. But I'll go ahead and write it for you. But the reason that we're actually interested in our intervals of concave up and concave down is because, and I already seen a couple of you guys do this on your quizzes, that you guys can actually graph them with this information. So what we want to do is in 4.4, and then actually in 4.3, they also ask you to graph in your homework, but in 4.4, it's really everything that you learned in 4.3 and everything that you learned in your algebra class about intercepts, vertical asymptotes, all of them together so that you have the tools to graph a function now. So now that you know calculus, I could give you any function, and because you know where they have minimums and maximums, how their shape is regarding concavity, concave up versus concave down, you now have the tools to graph your functions. So this is really cool, and it'll actually help you in the long run, especially if any of you guys are tutors, to know in the back of your head what a graph kind of looks like. I found it very helpful when I was a tutor because, you know, in the lower classes, they tell you to find the intercepts, but they don't actually tell you the shapes of the graphs, and knowing the shapes of the graph can tell you a lot about a function. So it's good to keep that in mind. So 4.4 will basically be a review of everything lumped together. It'll be one quick short video based on one example, maybe two if I have the time. But for now, I want you to try and practice. So let's have you guys practice this example. And then I'll close the video here. So I want you to practice on f of x equals x to the 4th minus 2x squared plus 3. I want you to go ahead and find the same thing as the last example. I want you to find your intervals of increasing and decreasing, find your local min and max, and your intervals of concavity, as well as your inflection points for this function. Should be easy, and then 4.4 should be a breeze. It's mostly review. Honestly, you might be able to even skip the video and do the homework on your own, I believe so, because given all the tools that you have, you should be fine. But I'll go ahead and make a really short video on it. It's probably going to be mostly example, not too much talking, because there's not much anything new that you will have learned in that section. It's getting everything you learn and putting it all together. So it's a pretty fun and neat section, I think.